first, let's have a look at the common scenario. So, family are having their vacation in Helsinki, and they decide to spend one day in a big shopping mall, local. The mom decides to go shopping alone, where the father and kids are going to find a restaurant to eat. After a while, the mom got outside the shop and then called the father. I just come out from Marimekko. Where are you? And then the father and the kids replies that we are currently sitting in Herzberg. So since it's their first time to come to this big shopping mall, they have no idea about the structure of the building, and the mom cannot find the way to Herzberg. In this scenario, indoor navigation service would be very helpful. However, there are a lot of outdoor location-based services, but this kind of indoor location-based service is still lacking. What are the challenges? First of all, up-to-date indoor maps are not always available, and conventional indoor mapping solutions requires professional tools and experts to operate them. Given the indoor map is already there, how to locate the users? Conventional solutions require pre-installation and maintenance of, for example, these Bluetooth beacons or these RFID tags or Wi-Fi networks. And another challenge is how to provide user-friendly navigation instruction to the users, given the map and the location are already known. A simple way is like show this simple go straight and then turn left and then turn right and so on. But this kind of instruction may make the user feel very confused. So can we provide a low-cost solution to these challenges? And can we utilize this nearly free crowdsourced data? It's common that the mobile phones nowadays are equipped with high-resolution cameras, and people are willing to share the exciting moments or beautiful scenarios with public. And this can be seen from the popularity of the photo sharing sites like Instagram and Flickr. From this figure, we can find that more than millions of photos are uploaded to Flickr every month. Yes, here I also use the same figure as a first presentation. This is a very famous SFM program. It's built Rome in a day, like using internet photos to reconstruct the 3D models of Rome city. So the technique in use is structure from motion. It mainly includes 3 steps. The first step is extracting the distinctive features from the images. And the second step is trying to find out the common features between these images. And the last step is called boundary adjustment. And the output of the pipeline is a 3D point cloud and the camera poses. This camera pose can be used to show where the photo is taken. So based on these features, using image-based localization is possible based on this SFM point cloud. So we propose to use these crowdsourced photos to provide an indoor navigation service. In this work, we present this using mobile crowd sensing-based indoor navigation to the user, and we address several challenges caused by the crowdsourced data. So first, let's have a look at the architecture of our system, iMoon. It mainly contains 2 parts. The first part is building sensor-enriched 3D model, and the second part is using these 3D models for indoor navigation. And first, we will use the crowdsourced photos to build and update the 3D model using SFM technique. And we also compile navigation mesh from the 3D point cloud. And second, we also use motion sensor readings from the smartphones to calculate the user trajectories. And we use the photos collected along the user walking trajectory to calibrate the trace. We also integrate the pedestrian paths recognized from the user trajectories to this navigation mesh. Third, we implement this fast image-based localization based on 3D model partitioning. And we also provide this user instruction by giving this text and visual information. Now let's take a closer look at the system implementation. Initially, we use a group of crowdsourced photos to build this initial model based on SFM tool. So in this work, we use visual SFM. It's a state-of-the-art SFM tool. And while the user is using our iMoon client walking around the location, and they will take more photos in order to get our localization or navigation service. We will then use these more photos to update the model. And this is a view of the 3D point cloud. These 3D points represent the obstacle information of the indoor environment. We will later use this to generate the navigation mesh. Based on the 3D point cloud, we will then detect the user trajectories and inject these trajectories into the 3D model. Our mobile client will read the accelerometer and the gyroscope and calculate the user trajectory based on data reckoning. And also, the photos collected along the user trace will be used as calibration points and calibrate the trace. At the same time, the mobile client will also collect these Wi-Fi fingerprints. Of course, these Wi-Fi fingerprints can be easily attached to this 3D model based on the user trajectories. And then we compile the navigation mesh. So here is this original point cloud. We first analyze the height distribution of these 3D points, and then we remove the 3D points representing ceiling and the floor. Also, we will remove the 3D points that are too close to the user trajectories. This is based on the assumption that there are no objects that are too close to the pedestrian path. So for the remaining 3D points, we will group them based on distance. So for each group of the 3D points, it represents an obstacle. And then we generate this navigation mesh based on these obstacles. So this is a 3D view of the navigation mesh of this part. So after that work, then we need to implement this image-based localization. So an ideal way is after user taking a photo, it will return where the user is and what the user is facing at. However, when the model in terms of this number of photos and 3D points will increase if there are more and more crowdsourced photos. So it takes time to load the model and implement feature matching in order to get the user location. In order to scale down this problem, we propose to partition the 3D model based on the density of the crowdsourced photos and the size of the 3D model. Also, since we have collected these Wi-Fi fingerprints beforehand, we can implement a Wi-Fi fingerprinting to find a coarse location of where the user is, and then we can get these small partitions, and then we implement image-based localization based on these small partitions. So here we give an example how to implement this small-scale image-based localization. So for a partition, we first know this coarse location, and we search the images within the range to get a group of photos. For these photos, some of them may face into the same 3D points, which are shown like these red points. So we only choose one of them in order to reduce the number of photos for feature matching. So after this process, we choose just a small group of the images, and then we use a user query photo to implement feature matching with these photos, and then finally get the user location. So given the navigation mesh, given the user location and the user identified final location, it's easy to implement a path planning. So in this part, we use a star-like algorithm to get the navigation path. So after generating this navigation path, we also try to provide a user-friendly navigation instruction. So this instruction consists of 3 parts. First, we try to choose a photo from the crowdsourced photo set. This photo should show the similar view what the user is currently looking at. And also, we draw the direction arrows on the photo to show where to make a turn in order to arrive at the destination. And accordingly, we generate these texts to show how far to go to this turn point and make the turn. We implement our iMoon prototype and test it in the lobby of our department. So this lobby includes a library, a buffet, and a long corridor. We used around 2,500 photos collected from the 5 volunteers and update this model. So this is a 2D view of the point clouds. And this is an official floor plan. So basically, they have similar outline, and the distance error is around 0.5 meters. And we also find that the official floor plan cannot really reveal this ground truth. So you can see this is a library, the current organization of the bookshelves. But in the official floor plan, it's like this. But in our 3D models, it can show it correctly. This is because it always uses newest photos uploaded by the crowdsourced users and update the model. So this is the generated navigation mesh based on the 3D point cloud. The average distance error of these obstacles are around 0.78 meters. And in order to evaluate the indoor localization performance, we collect another group of photos. It's 2,220 photos from these 185 measurement points. So for every measurement point, we use this self-designed toolkit to collect 12 photos. It consists of a laser rangefinder, tripod, and our iMoon client. So after taking the first photo, it will rotate 30 degrees and take a second one, and so on. So for each measurement point, it will take 12 photos for testing. And this shows how to calculate the ground truth. This is a toolkit, and we have pre-tagged the reference point, which has accurate coordinate. And then we will calculate the coordinates of the toolkit as a ground truth. Since our iMoon localization is a combination of Wi-Fi fingerprinting and image-based localization, so we make a comparison between this iMoon and the simple image-based localization and the Wi-Fi fingerprinting localization. The first metric is how many measurement points can be localized. We define this as hit rate. So from the table, we can find that both the image solution and the iMoon can localize around 95% of the measurement points. Of course, Wi-Fi can always localize it. Just the distance error is larger. The reason that iMoon can not locate 5% of the measurement points is because some of the environment is changing, and some of the photos are facing on some featureless, like the blank wall. And then let's have a look at the localization accuracy in terms of the location error and facing direction error. So both iMoon and image-based localization can locate around 90% of the photos with a location error less than 2 meters and the facing direction error less than 6 degrees. And Wi-Fi has a relatively larger distance error, but since it can always has a 100% hit rate, so iMoon can utilize this Wi-Fi fingerprint as a backup solution if it cannot return an image-based localization. And now let's have a look at this response delay. Yeah. Wi-Fi can return the localization application very immediately, like within 0.7 seconds. And for image-based localization, it takes quite a long time. It's because we are using visual SFN. It needs to load this large 3D model, and it takes time to load. And also, it will use the image to implement a feature matching with a large number of photos. So with iMoon, we first use Wi-Fi fingerprinting to find a small partition and then implement a small-scale image-based localization. So the response delay decreased to around 4 seconds. So based on the analysis and the evaluation, we found that it is possible to utilize these crowdsourced photos and the sensor information to provide a relatively high performance indoor navigation service to the mobile user. Regarding the future work, there are several interesting things we would like to do. The first, track the users use this non-perfect map. Actually, it's a map built from the crowdsourced data. And in order to improve the user experience, we also want to further decrease the response delay. And we also want to measure the user experience and utilize this text and sign information extracted from the crowdsourced images for example, this application like augmented reality. And as a conclusion, we first propose a low-cost and a full-assistant solution for indoor navigation. And then we utilize these crowdsourced photos and the sensor information to build the sensor-enriched physics model. Then the evaluation results show that our indoor localization can achieve a high accuracy but low latency. And finally, this is the advertisement. We also will show our demo in the demo session, so you're welcome. Yeah, that's all of my presentation. Questions?